So we've covered some of the more complex sigma notation identities and properties and formula associated with them. What I'm going to give you here, I'm going to give you just a couple of questions relating to that material, bringing in these ideas plus some of the ones we've done before. What I want you to do is read the questions, pause the video, have a crack at them, and then come back and see how you get on. So here you go. So I want you to express the first one as a function of n without the sigma notation, so similar to the one that we did in the video. And then I want you to prove this identity. So I want you to prove that the sum of r equals 1 to n of r cubed is equal to this here. So something for you to think about. So pause the video and have a crack at these. So the first of the two questions. So I want the sum from r equals 1 to n of this written exclusively in terms of n. Well, the first thing we have to do is multiply out what's in the bracket. We can't do anything until we get rid of those brackets and see what we've got. So I get the sum from r equals 1 to n, in this case of 4r squared plus 4r minus 3. Then we separate it out into each term and use the properties and the rules that we know from before to manipulate it and see what we can get in terms of n. So if I then split it all off, I get 4 times the sum from r equals 1 to n of r squared plus 4 times the sum from r equals 1 to n of r, take away 3 times the sum from r equals 1 to n of 1. Now I know what all three of these are equal to n terms, so it's substituting those in and then manipulating it about. So I know then that's going to be 4 times 1/6 n bracket n plus 1, 2n plus 1 for the first term, plus 4 times 1/2 n bracket n plus 1 for the second term for the r, and then minus 3 n for the final term. So now I just have to multiply out these brackets, simplify it all down, and see what we get. So for this first term, I end up getting 2/3 n bracket 2n squared plus 3n plus 1. I've then got plus 4 times 1/2 is 2, so I get 2n squared plus 2n there, and then I've got minus 3n here as well. So I've now got these parts all multiplied out. I just need to fix this first bracket, then I can manipulate it from there, gather like terms, and see what I get. So if I multiply out this first one, what I get is 4/3 n cubed plus 2n squared plus 2/3 n. I've then got plus 2n squared here. I've then got plus 2n minus the n. Take away n from there. So let's gather all the like terms together and see what we can do with it. So I've got 4/3 n cubed. I've got plus 2n squared plus 2n squared. So I've got plus 4n squared there. I've then got 2/3 n, take away an n, so I've got minus 1/3 n. So from that I can take out a common factor. Now I want to get rid of the fraction, so let's take out 1/3, but I've also got an n in each term, so I'm going to take out 1/3 n. So what that leaves me with is 4n cubed plus 12n squared minus 1 in the bracket. Now if I was to do b squared minus 4ac for this one, what I'd notice is I could factorise that bracket, but I actually wouldn't get anything involving whole numbers, so I'm just going to leave it as it is. That right there, if I substitute a value for n, I'm told how far the sum goes, I can tell you straight away using that what the sum for it would be. The second question was slightly more interesting. What they wanted you to do is prove that the sum from r equals 1 to n of r cubed was equal to that. So that's what I'm going to be doing with this one. Well, let's think in a similar fashion to what we did before. So before we looked at the next highest power of the bracket of r plus 1. So let's look at the same sort of thing here. So let's look at r plus 1, this time to the power of 4. Now I know that if I was to multiply that out, I'd get r to the power of 4 plus 4r cubed plus 6r squared plus 4r plus 1. Now if I was to then split that and take the sum from r equals 1 to n of both sides of that, What I could then do is take this side in a similar fashion as I had before, split each term up on its own, and use the rules that I now know in order to manipulate it. So if I split it up, I'd have the sum from r equals 1 to n of r plus 1 to the 4 on this side. That wouldn't change. That's then going to equal the sum from r equals 1 to n of r to the power of 4 plus 4 times the sum from r equals 1 to n of r cubed plus 6 times the sum from r equals 1 to n of r squared plus 4 times the sum from r equals 1 to n of r, and then just plus the sum from r equals 1 to n of 1. Now I just use the properties I know in order to manipulate it. Now similarly to before, let's stick all the r to the power of 4s on one side, and let's substitute in what I know. Now this one here, the one with the r cubed, that's what we're trying to find, so it's quite important that that stays. We know the property for r squared, we know the property for r, and we know the property for the 1. So let's substitute all of them in as we manipulate it. So my left hand side becomes sum from r equals 1 to n of the r plus 1 to the power of 4, take away the sum from r equals 1 to n of r to the power of 4. And then on the right hand side, what I'm left with is everything from here. So I get 4 times the sum from r equals 1 to n of the r cubed, and then I just substitute in the properties for each of these. So I get plus 6 times 1/6 n bracket n plus 1 bracket 2n plus 1. I've then got plus 4 times what I know for the r, so 4 times a half n bracket n plus 1, and then I've got my final one here, quite simply, plus n. So what I now do is I manipulate this bit here and simplify it down, and I can use the property I know about this side, get everything else in terms of n, and then make this the subject of the formula. So if I'm just going to focus on this little bit here just now, multiplying out all these brackets, so 6 times the 6th is 1, so I get n bracket 2n squared plus 3n plus 1. This one here, multiplying all that out, I then get plus 2n squared plus 2n. 4 times a half gives you the 2, so that's where that goes. Then I've got the plus n there. Multiplying this first bracket out, I now get 2n cubed plus 3n squared plus n plus 2n squared plus 2n plus an n. Now I group everything that's got a like power together and simplify it down. So I've ended up with 2n cubed, I've got 3n squared and 2n squared, plus 5n squared there. I've then got plus n plus 2n plus n, so I've then got plus 4n there. This side here, I use the property, and I can rewrite that side as n plus 1 to the power of 4 take away 1. So what I know then is that equals this here, the r cubed, plus all of this. Now what I want to do is make this the subject of the formula. So I can rewrite it so that I get 4 times the sum of r cubed, where r goes from 1 to n. What that equals is this, take away all of this. Well, I know what the n plus 1 to the power of 4 is, so let's just write that in as we go. So I've got n to the 4 plus 4n cubed plus 6n squared plus 4n. Now I would have a plus 1, but I've then also got a minus 1, so I can just miss that off. I've then got take away 2n cubed, take away 5n squared, take away 4n. If I simplify all of this on this side here, what I end up getting is I get n to the power of 4 plus 2n cubed. I've then got 6n squared take away 5n squared. I've then got plus n squared. I've then got 4n take away 4n. That leaves me with nothing. So if I then take the 4 across here, what I end up getting is that the sum of r cubed is equal to a quarter bracket n to the 4 plus 2n cubed plus n squared. Great, we've got that, but we've done all that work for nothing special. However, let's manipulate it a little bit and see what we can do. Because what I can then say is that this side here is the equivalent of a quarter n squared bracket n squared plus 2n plus 1. Now this here can be written as n squared bracket n plus 1 squared, so two squared terms, but the quarter can be written as that as well. The quarter can be written as 1/2 all squared. So all of this here, what I can rewrite that all as is that the sum of r cubed from r equals 1 to n is equal to 1/2 squared n squared bracket n plus 1 all squared, and if I take the squares out and manipulate it from there, that then equals the sum from r equals 1 to n of r cubed is equal to, in a big bracket, 1/2 n bracket n plus 1 with the whole thing squared, which is exactly what it wanted me to prove at the start. Now that's the equivalent of here, but I've had to manipulate this from there to get it back up into the form that I wanted at this point here at the top. So it's a little bit more work at the end, but actually it's quite a nice result. Now one thing you actually might notice about that is that this here is the equivalent of the sum from r equals 1 to n of just r. So another thing you could write from that is that the sum from r equals 1 to n of r cubed could also be thought of as the sum from r equals 1 to n of r all squared. So that there's also another way you see it written sometimes in textbooks and exercises and exam work. So bear both of those in mind. They're the equivalent to each other. So it's quite a nice, neat little trick. There's lots of different ways to manipulate it using these properties. All of these are things we have to remember. So the sum from r equals 1 to n of 1, r squared and r cubed, all of these have to come to us and we have to make sure that we remember them. Now sometimes it's easier to remember this bit I've just written here about the r cubed being the r squared. Sometimes it's easier to remember that, so you've only got 3 main formulae to remind yourself of. Just make sure you can prove each of them and you can manipulate and take something so that you're able to substitute these in and you can write it exclusively in terms of a single variable n, which is the limit of the sequence.